Good morning, everyone, and I hope you all have enjoyed the Belgian beers and the fries last night. I will introduce myself. I'm Michel Drenthe. I'm working for OpenWeb as a Java developer and mostly working on OpenCMS Java-based content management systems.
And I'm Ivor Boers. I'm also a Java developer for OpenWeb. I have no experience in IoT, but I am a mechanical engineer by education. And, well, I love sailing. So let's have an adventure in autonomous sailing.
Indeed. So we like you to introduce to our journey. And our journey starts during Christmas last year, 2017. Where we had a nice talk with our CTO about the Transit Challenge, there where you can cross the ocean from America to Europe or Europe to America, and then we would follow. The conversation continued on, and while we were talking, we came to the discussion about Microtransit Challenge, and that we could be the first to finish it. A small introduction to what is the Microtransit Challenge. As you might already have guessed, it's about crossing the North Atlantic. And yeah, it's a challenge that has been set up in 2005. The first participant joined in 2010. The rules are that you cannot have a boat longer than 2.4 meters. There are two categories, one of sailing and one of non-sailing. And within these categories, you have the unmanned division and the autonomous division. We are joining the autonomous division, and how it works is, while the unmanned version, while it is sailing, you can still send coordinates towards the boat, and this will provide you the boat with new coordinates. And the autonomous version, you only can set an endpoint on the finish line, and the boat has to get there. So, what are the routes? We have the northern route, as I told before. It is the one that goes from America to England. And the other southern route goes from England to the Caribbeans. This challenge has some participants, and one of the successful participants, at least in launching boats, is the team called Joker. They have launched around 8 boats, and they graduate on getting more mileage. And their longest one was about 853 kilometers. Small note, probably after 50 kilometers, it already was broken, and it was going with the tide. 2017 was the last known launch from them. And during their launch, while they put the boat into the water, a big wave came, and the mast broke. So they got it into the news. So this year, there were also a couple of attempts, and the one with the blue sail is the one that does the unmanned version, and he got to the finish line. And the yellow one is the one that does the autonomous version, and it got lost. And to give you a presentation on how it is going, the red one is the unmanned version. So there you could see he got to the finish line, and the purple one probably sank. So what do I need to do when I'm going for sailing?
Yeah, we have a challenge to go sailing. So what exactly is sailing? Therefore, a short introduction, some terminology. First of all, this is the kind of boat that we're talking about, kind of like our little boat over there. These are the technical drawings. If we view them from the top, the boat, we can see it has port side, starboard side. Never ever talk about left and right on a boat. The colors are used for navigation lights, for example. Let's view the boat from the side. Just some terminology to get you into our presentation. We have a hull, which is the main part, of course. Under the waterline, there is the keel and the rudder. Now, the keel is used for keeping the boat upright, and the rudder is used for steering. Steering a boat is somewhat more difficult than steering a car. Steering a boat, the boat will not always immediately change direction, like in a car. And it depends on circumstances, of course, like the waves or the wind. Now, if we look above deck, then there's a mast, obviously. Attached to it is the boom. And we have the mainsail, which is attached to both the boom and the mast. And there's a second sail called the jib. So we've seen there are 2 points of control here, which we need to automate. There's a winch for adjusting the sails, adjusting the angle of the boom. In a normal boat, there are 2 lines, separate lines. In our little boat here, both lines are attached, so you have 1 winch to control the line. For steering, we have another servo, and we can use the servos for controlling both controls. So what exactly is sailing? How does that work? Well, sometimes I think it's kind of magic, but actually it's like the wings of an aeroplane. A sail will create lift because there's a different velocity of the air on the front and the back side of the sail. Just like in a plane, the wings will create a lift upward, and here it will create a lift which is more to the front of the boat. Now the jib, well, both sails obviously will work to create lift, and the jib will further enhance the efficiency, and it does that by reducing turbulence on the back side of the mainsail. So it's keeping the airflow attached and thereby increasing the efficiency of the mainsail. So what's important is adjusting the angle of the sails to the wind direction relative to the boat. So it's keeping the airflow attached to the sail and, thereby creating the forward motion. And it works somewhat like this, explained in vectors. So suppose we have the wind direction from the side, then the force generated by the sails will look something like this blue vector here. It has 2 components, a sideways component which is tilting the boat, and it has a forward component which is what's propelling the boat forward. But if you look at this picture, then you say, well, why doesn't this boat just drift sideways? That's because of the part that's the boat that's under the water, like the keel. And the keel is also an aerofoil shape, and it's generating a force opposite to the wind direction. So its resulting vector is the red one here, which is what's moving the boat forward. So now we know a little about sailing, our terminology. Let's discuss the first meeting we had with our team.
Yeah. So we just arrived in the month March now, and we set up the first meeting. We deliberately put the first meeting on a Saturday morning because we wanted to see how many people were willing to put in their free time into this project. The first meetup was a great success. It was such a success that we came up with a plan to divide and conquer the whole project, so we could finish it in 1 year. As you can see to my left and your right, you can see there were all kinds of things we were preparing for, repairing the boat, changing the boat, change some course, be able to calculate the wind, the angles, and navigation. The next step of our plan was to start small, like Agile. We start small, we make it incrementally bigger. So, and we wanted to have a boat. So near our office, there's a small lake called Loosdrechtse Plassen. And this lake is manageable. We can see the other side of the lake. So we can just put the boat in, test it. If it fails, we can retrieve it from all the sides and carry on with our progress. Then the next step would be we could go to the IJsselmeer, because it's much more bigger and it has almost sea-like conditions, except the waves are less high. Then we would go for the North Sea, where we would go from Netherlands to England, and as the last step of the project, cross the Atlantic. So, during our first meeting, we also came up with a couple of decisions, which is we have lying a lot of raspberries in our office because we are doing IoT. And with them, we have also a lot of groove shields, which makes it easy to connect new sensors to them. During this meeting, we also decided to go for Python, because we are all Java developers. And use TensorFlow, because a lot of people say, when you're doing machine learning, you should do TensorFlow. So that's what we picked. And the last and most important part is we should get a boat. So we set out our goal, and now we were planning to get there, and we're expecting some things to happen. So, but we are still in a good pace. So, Ivor, tell us about buying the boat.
Yeah, obviously we needed a boat, and we needed a boat not directly for the ocean. We needed a boat that would do some testing. It was easy to adopt. It would fit our Raspberry. We could add some sensors to it, and obviously it needed to be smaller than 2.4 meters as in the regulations of the challenge. Now we wanted a boat that we could go sailing quickly. So we thought we'd take an RC control boat and just gradually replace that controls with our own controls. And quickly we found a class of boats, the one that you see here, which is called a K-class, which is a class of boats that's, has a large community in the Netherlands. Almost every weekend there are sailors doing match racing. So it's actually 1.9 meters long. It has RC control, so it fit perfectly. And because of the large community, there are spares available, but there's also second-hand ones available, and soon we found one. Now, when we bought it, as you can see, it was red from the fire department, including stripes. As you see it now, it's painted in our company colors. We needed someone to do the sanding and repainting. But soon we appointed a volunteer to do that job. First we looked at the electronics inside, and we found that, it was quite an old boat. All the electronics, they didn't work anymore. The battery was even older, I guess. Not much left. Controls didn't work. We had to replace all the electronics inside. We had to buy new remote controls. And as we were doing that, we found that it was quite an old version of the K-class, and the newer models had a more powerful winch. We were busy with repairing the electronics, so we just also replaced that with a newer model. So, as you can imagine, this whole process of fixing the boat has cost us a lot of time, which, we didn't plan to. But hey, we've actually fixed the boat. It's in our company colors, and it's, time to put some hardware on it.
Yeah. So, small note, we did this in parallel. So the boat was repairing during the talk of Ivor, and at the same time, me and our CTO were working on getting the hardware ready. So, what do we need to get the boat into a completely autonomous state. We should be able to control it, so we need some actuators to be able to control the winch and control the rudder. We need to have some sense of the outside world or the state of the boat itself, so we need all kinds of sensors. We have the Raspberry, of course, that is controlling everything, and the regulations of the microtransit states that we should put lights on them, and be able to communicate, and a communication device. One of the rules is, for example, that we have to at least report within every 6 hours that our current location. If we fail to provide that information for 10 consecutive days, then we are getting disqualified. And if we don't miss a couple of them, when the total of misses reaches 15 days, then we are disqualified as well. So we have a lot of sensors at the office. So what can we use? We need at least a compass, because we need the heading of the boat. We need a GPS, a gyroscope, and a lot of angle sensors. So to start off with the GPS. A GPS is quite an interesting device to connect to a Raspberry, especially because it is actually using its own protocol. To be exactly, there are 7 lines within them, and we are actually only interested in one of them. So figuring out which message we have to use and how to decipher them and comply with the encodings that are telling us if the line is correct was a bit of a hassle, and is also to configure the Raspberry itself to be able to communicate with this device. But after we changed the settings and we got it working, so we have a GPS now. Then we get to the compass. The compass was for some reason much easier than the GPS. It was just connecting it, read out the memory allocations that are within the chip, and give us the reading of the heading. The funny thing about all these chips are that they not come with only one sensor. This one, for example, comes with also the ability to get a gyroscope. And that's quite handy, because it tells us what tilting the boat is getting into. Next of it is the accelerometer. The accelerometer tells us the speed the boat currently has. It also has a gyroscope, and for some reason this sensor also has something called a step counter, so we know exactly how much steps we do with the boat. Next is the angle sensor. So what you see here is before we assembled it, the angle of our main mast, and actually, to be precise, the boom of the mast. The boom has a certain angle, which we need to get it right to be in the wind, and this one provides us with the information on what the angle will be. The angle sensor itself has a limited range, but the mast, as you can see, the sails can't turn 360, so we are all safe. Next is our wind sensor. This is one we are currently still working on. This is a traditional wind sensor that gives us the direction of the wind, and below tells us how much flow there is. This one is too bulky for our boat, so we came up with this solution. So this is an absolute sensor. It has the ability that when it drops power or loses power, that when it recovers, it still gives exactly the position it is in. Where the other angle sensors, when they lose power, they just start at 0, and you have to go left and right, and then you have to reset it completely. But the problem with this one was there was too much friction on the sensor itself, so we had to put almost twice as big vane on top of it as the left one. So we were looking to a newer version, and this one, it's not the one that's going exactly on the boat, but it will be a much smaller version, but this one gives you a precise look on how it works. So there are 4 ultrasonic microphones you can compare them to, and by the flow of the wind, this one or 2 microphones will produce static noise, and the louder the noise is, the more wind there is, and from the direction the wind is coming, the microphone that picks it up, you know the wind is coming from the opposite direction. Now, you may be wondering, why do we have all these sensors, some of the sensors duplicate of them? And that's actually to get our accuracy at least higher. We can, because we have more of them, we get more accuracy, because more sensors tells us where it thinks they are. What node we cannot, the one thing we cannot do is increase precision, because of we have to calibrate it, and we are not on the boat. So this is all about the hardware. So can you tell about the software?
Yeah. We thought about an architecture for the software. I'm not going into the details of the software. But we have, as discussed, we have all these sensors which provide data. We also have the communication device, because we're allowed to, for example, get weather information or other kinds of information which is publicly available. And we put all this data into our data service. And this data service should provide the rest of the software with valid data at all time. We don't want our boat to fail because there's some invalid sensor. So when the data service gets the data, it will test if it's valid data actually. If it's not, it will retry, or it will retry a backup sensor. And even in maybe some worst case scenario, if it can, it will try to guess based on previous values what value to give. So this data is always a valid set of data. And we will provide this to our navigation service. Now it's obviously we need to get our boat to the start line. We have to sail 40 nautical miles before even reaching the starting line according to the rules. And then, well, it's passing 5,000 kilometers on the ocean, somewhere on the finish line. So we need a geofenced area in which to navigate to the finish line. And, well, based on current conditions, weather conditions, maybe expected weather, our boat needs to navigate the ocean. So this navigation will provide a course, which helms control, which is actually a combination of the controlling of the rudder and the winch. So the helm control will get the course to take from the navigation, and it will adjust the rudder and the winch, the sails, to be able to sail this course. Now in this architecture, you can see there are different parts. This navigation is, well, it's relatively slow. It's no use to recalculate a course every second. But the helms control is something you need to control the boat itself, which is a fast loop. And maybe even in future we'll put it in a different controller of itself. Now we started off by implementing the data service. So that was our first task. Just get the data from the sensors, put it in a database, and later on we implemented navigation and helms control. First off, we used traditional algorithmic programming. In future, these are the parts that we like to replace with machine learning to take the best route available for navigation, and also maybe adjust the sails by using, I don't know, maybe a camera or something to see if sails are well adjusted. Well, as I said, first of all we had the data service, and when we finished that, we could go sailing, basically, with our remote controlled boats.
Yeah. So we now reached the month June. And we are getting there. We are having our boat that's completely repaired. It's not painted, but it's working. We have some basic software that starts reading out all the sensors, not controlling the boat, but at least reading out all the sensors, providing us with the data sets we are going to have when we are sailing. And to give you an impression how it looks like, this is the brain of the boat, as we call it. It's a pencil box where you put in the Raspberry, and we have this small box for a power bank, and we attached all the sensors with it with electric tape. And beneath it, there's a big power bank that we were willing to test. Then we drove to the nearby Loosdrechtse Plassen, and then we set up the boat, control it again, are sure that everything is rolling, and yeah, we put it into the lake. So, some facts about this lake. This lake is built nearby a chemical waste hospital chemical waste, and thereby this lake has got the properties it never can freeze anymore. So we can even test it during winter time. The only thing is you should not swim in it. No. This is our first trip. There it is. And this is someone that was nearby and that was willing us to provide us with the information, or at least with some footage of our own first sailing attempt. What you can see here is that it's just sailing fine. As you can follow the line at the most right, down, yeah. There we got into problem. The sail got stuck. Apparently we didn't know about how we should keep the tension on the lines toward the mast. So the line became underneath the winch, and then we lost control. Except we only had a rudder. So we managed to get it, retrieve it back on even the place we were still standing. So we didn't have to swim. Next week, we were going to do this over, and then we were fully prepared. We set up everything, batteries were fully charged, and we thought, let's go for duration tests. As you can see, it provides at least with a lot of data. The problem is when you try to draw it, it's one big ball of mud, or at least wires. Interesting fact is that you can sail at least for 8 hours, and we as developers that are not getting out there as much aren't that protected against the sun. So we got sunburned. But okay, we can cross our small lake again, and we are getting there to get to the Atlantic, but first, of course, the other smaller steps, and also more to autonomous. But crossing the Atlantic, what will it bring? So,
yeah, we know we can cross a small lake, but crossing the Atlantic is some other challenge. Also given the fact that it's been, 10 years for this challenge, and only one boat ever crossed the ocean, and that was even not autonomous, but unmanned. So there's a lot of challenges on the Atlantic. And, well, what most people think of course, is big waves and stormy weathers. And obviously, certainly when we take the northern route, this is what our boat has to survive. And these are really rough conditions. It's not just the water, it's the salt, it's the sun, continuous wind. These are things that are really rough to any material. So having a lot of wind is not only the only challenge. Obviously, our boat needs to be sturdy enough to survive this, but another challenge is when there's no wind at all. And, it's not going to break our boat. But it's a different kind of a challenge. So when there's no wind at all, a boat doesn't have any speed, and thus it can't steer. So if our navigation service will recalculate a course, and the rudder will be controlled by servos, nothing will ever happen. So it will use a lot of energy, maybe, and it's getting nowhere. So what actually needs to be done in these conditions is, well, just save energy. Save energy for when we really need it, when there's wind. So that's something to think about. This is another type of challenge. There's a lot of plastics in the ocean. A large part of the plastics is fishing nets. And I guess most boats will just sail into it, and maybe it gets stuck, but they can continue. Our little boat will get stuck in these kind of fishing nets. So that's something to think about. And obviously, I guess most of you heard about the Ocean Cleaner project, which is a project that has recently started on the Pacific, and they're trying to catch all the plastics and bring it back to land and recycle it. But the Pacific Ocean is not the only place that there's a lot of plastics. As you can see here, the North Atlantic also has a lot of plastics floating around. So please carefully dispose of your plastics here. It will save our boat. So something else might pop out of the water. If we have no plastics, maybe a whale will crash on the boat. There's not much we can do about that, I guess. It's just bad luck. However, there are some things that we can expect. I mean, oil platforms, we know beforehand where they are, and we can program them into our geofenced area, just like islands or sandbanks, or maybe even military training grounds for submarines. They are on the ocean. Another obstacle might be the moving parts on the ocean. Not only ships, but also icebergs. There is public information available for moving icebergs, and maybe we can even receive these and do something with it. However, boats might be a problem, or the rules state that we should avoid a collision because it says so in the international regulations. And we thought about it for a long time. I mean, most autonomous projects will have a LiDAR on top somewhere scanning the environment. Looks kind of cool, but it actually doesn't work when there's a moisturous environment. These laser beams will just get diffused by water drops. So that doesn't work on the ocean. What are the other options? Well, maybe a radar, but it's quite bulky. It needs to be high up to be able to look over the waves. Then there's 3D video. I think it will cost a lot of processing power and energy, and we have a tiny boat with a few solar cells, so we need to be careful with how much energy our boat's going to use. And we thought about it. Well, what's the chances of actually having a collision, and then having a collision which will cause damage to our boat? And chances are slim, but hey, rules state that we should. So actually we read the international regulations, and right, forgot one thing. Well, we can avoid boats, not just by using these fancy techniques, but there's something called AIS. Every boat that's on the ocean, and you can see there are a lot, will publicly provide its current position, its heading, its velocity. And you can look it up on marinetraffic.com, and you have a screenshot like this. And this is probably something we can use. I'm not sure if it counts as active obstacle avoidance. So the rules state that if a vessel doesn't have any persons on it, it doesn't have any cargo on it, then it counts as a buoy and not as a vessel. So it doesn't actually need active obstacle avoidance. So combine that with our calculation of probability of a collision. We said, well, our boat will be just a buoy. So in short, a recap, things we need to prepare for is the really rough conditions. Now this, as we said before, this is a boat for just training and testing. If we go on bigger waters, we obviously need a new boat, which is built for other conditions. We need to save energy. That's going to be quite an issue, as we don't have really that much area for solar panels. Active obstacle avoidance is something that we will not use. Well, as for now, anyway. We call our boat just a buoy, and then we can comply with the regulations. So these are just future plans, but hey, where are we now?
Where are we now? Oh, we have at least a working boat, and it can sail, and it has some software already starting towards being autonomous. We're still missing some parts to get it fully autonomous, like the one that controls at least the rudder and the servo. That one is still missing because we have to bridge over a certain voltage to another different kind of voltage within one boat, and we are still researching how we actually know how to do it. We only have to get the right devices for it. Sailing on the water goes perfect as long as you use remote control. And we almost got all the sensors. Like the wind sensor is now on transit towards us, I believe. And it should arrive soon. We have played at least with knowing that we have to set it up by Bluetooth. And apparently when we had set up our Raspberry the first time, we just disabled almost everything that has something to do with connectivity. So we had to re-enable them. And we are collecting data. So we have to go out of sailing much more often so we can collect data, and then we can also start to train our machine learning, actually. And we are still figuring out how we have to do that. So, as I showed you in the beginning, we had set out our goal, and we have run into a lot of these interesting challenges. One of them was the wind sensor. We still have to figure out how to mount solar panels on them, or that we even mount them on this one. We also still have to figure out how we going to provide the microtransit organization with the communication. They told us, or they didn't tell us, but all the other participants are using satellite phones. And we guess there will probably some more problems on its way. Moving the boat to a conference is not a good idea, actually, but it looks nice. And that's actually the end of our talk. So are there any questions? Yeah?
You already calculated how much power you need and how much solar panels.
The question is, have we calculated the amount of power we needed? We only looked up the statistics of the power consumption of the Raspberry itself and compared it with our batteries, and then what should we get as solar panels. We still don't know how much it's used. We're planning to write a part of software to at least calculate that one. During our duration tests, after 8 hours, none of the lights were gone, so we couldn't measure how much power we had used.
When are you planning to do the trip?
on the ocean. The question is, when are we planning to launch it on the ocean? Our initial goal was to launch it this year, but it didn't happen. We hopefully get it next year fully autonomous and then start increasing the range. But we are not exactly certain, and the only thing we know for sure is that in January the rules of the microtransit will change slightly, and we have to look into the rules of the challenge again.
Have you considered wind energy to charge your power bank?
The question is, did we consider wind energy to power our boat? Not. I didn't, but it sounds like a good idea. But the thing to keep in mind is we are moving with the wind as well.
Yep. Same time you can use it to charge your power bank.
Yeah, that's true. We're going to probably look into that one. Indeed, yeah.
Wear and tear is a big issue in ocean racing. What materials are you anticipating for your sails and for your control rigging?
So the question is, what materials are really degrade really fast on the ocean? Heavy, rough conditions, the sun and salt. So what materials do we plan to use? We're not planning that far ahead, actually. There are some ideas, however. The boat that we've shown that have participated this year, so one has a solid sail, and the other one does have a sort of a flexible sail. So we see that both options are possible, should be possible. There's one interesting project which has autonomous boats like 7 meters long, not for this challenge, but they use also a fixed sail. And maybe that's a good idea for, because it looks really sturdy. So that. Other questions? Okay.
Thank you.
Thank you for joining.
Yeah.